Now that we're more familiar with the modulus and the argument of a complex number, we can elaborate a little more on the argument part and also in notation that we're going to use for complex numbers. So let's start with notation. We are going to introduce two ways to write complex numbers in polar form. Now the first way is going to be called cis form. Now, cis form is a definition, so let's work it out. Our number was originally written as x plus I, y, and previously we discovered that I can write x as r cosine of the argument, and y I can write it as r sine of the argument, so that when I substitute into my complex number, I get r cosine of theta plus I r sine of theta. Now, so far is what we talked about previously. Now, what I want to do new is I want to take the r out as common factor. R, common factor of cosine of theta plus I sine of theta. This number that I get in this bracket is a complex number with magnitude of 1, and it is purely a function of the modulus of the number. It's purely a function of theta. So I can define the function cis of theta as cosine of theta plus I sine of theta, as a short way of writing all of this. So in that way, my number in cis form is going to be z equals r cis of theta, with the understanding that cis of theta is going to be equal to cosine of theta plus I sine theta. So if at any point I want to go back to Cartesian form, all I have to do is substitute this expression, substitute the angle, and calculate to get the specific values for x and for y. Again, this form is called cis form. Now there is a second form, and that second form we can talk about it a little bit more when we introduce polynomial expansions for functions. So that's going to be a few units later. However, you should be familiar with this notation as well. And the second notation is Euler's form. Euler's form is going to use the following definition. The same number, z equals r cosine of theta plus I sine of theta. We are going to call this unit number e to the power of I theta. So instead of calling it cis theta, we're calling it e to the power of I theta. And these two definitions are going to have very, very similar properties. So they are interchangeable. In this way, the number z is going to be written as r e to the power of I theta. Let's work a few examples. The first example that we have here is example number 3. Write the number z equals 3 cis of pi by 3 in Cartesian form. For this, we just need to substitute the definition of cis, and that is going to be z equals 3. Now, cis is cosine theta plus I sine theta. So, cosine of pi by 3 plus I sine of pi by 3. In radians, pi by 3 is equivalent to 60 degrees. So it's the same as 3 cosine of 60 degrees plus I sine of 60 degrees. Yeah? You should be able to work in both. Now we know that the value of cosine of 60 degrees is going to be 1/2. And the value of sine of 60 degrees is going to be √3/2. So the final answer in Cartesian form, this number is 3/2 plus 3√3/2i. Our next example, write the number z equals e to the power of I pi in Cartesian form. We know that e to the power of I pi is going to be cosine of pi plus I sine of pi. Now pi is equivalent to 180 degrees. So this is going to be cosine of pi is -1 plus I. Sine of pi is 0. So the answer is e to the power of I pi is equal to -1. Let's introduce one more concept, and this is related to the concept of the argument. So let's consider the number x plus iy, but let's consider 4 different cases. There are situations when the number z is going to fall in the first quadrant. Sometimes it will fall in the second quadrant, other times in the third one, and other times in the fourth one. Now, the key to polar form is that you should be able to identify in which quadrant each of the points are located. And you can do so by considering the signs of the imaginary and real part, or by considering the magnitudes of the argument. There is a second way that you can get a hint, and that is through the concept of the principal argument. Now, the argument, as we defined it before, is an angle that goes from 0 to infinity. So you can take 1,000 degrees, 1,000,000 degrees, you can take 70 degrees. But the principal argument is only defined between -pi and pi, or between -180 degrees and 180 degrees. There's no other option for the principal argument. We are going to denote the principal argument as the angle argument with a capital A of z. Please notice again that this is not going to be necessarily the same as the argument of z. So the principal argument, we said, is going to be defined for values of the angle between -180 degrees and 180 degrees, or between -pi and pi. However, the argument, as we learned it before, is going to be any value as long as it's bigger than or equal to 0. So there is a very special difference. Graphically, how do I know what is the argument, what is the principal argument? In the case of the first quadrant, the argument is going to be measured from the horizontal axis upwards. So this is going to be the argument of z. And the principal argument is going to be also measured from the positive horizontal axis towards the direction of the point. So in this case, both match, they are both the same. So this would be the principal argument. So from the horizontal axis, I go towards where the point is located. Now in the second quadrant, the argument of the function is going to go counterclockwise towards the number like this. So this is going to be the argument of the number set. And the principal argument is the same definition. From the positive horizontal axis, we go towards the point. So that is going to take me in this direction. So For the second quadrant, the principal argument and the argument, they match. They are the same value. Now things are going to change for the third and fourth quadrant. In the third quadrant, the argument, as we have been using it, starts from the positive axis and goes counterclockwise to the position of the point. And this will give us the argument of Z. However, the principal argument is going to take always the shorter route. I'm going to take from the positive axis, but this time I'm going to go clockwise towards the number. And then this is going to be the argument, well, the principal argument of the number Z. So now you can see the difference. The principal argument will always take the shorter path. So you're always going to count the shorter angle. In the fourth quadrant, we have a similar situation. The argument, as we had it before, goes counterclockwise all the way until where the point is. This is the argument of Z. But the principal argument is going to take the shorter route. It's going to take from the horizontal, positive horizontal axis towards the point, but following the shorter path. So this is going to be the principal argument. Now notice two things. We are defining angles that go counterclockwise from the horizontal axis. We call those angles positive. So the argument in blue is always going to be a positive angle. It's always bigger than or equal to 0. However, the argument, the sign of the principal argument is going to depend on which quadrant we are measuring. So for quadrants 1 and 2, we are measuring the principal argument counterclockwise from the horizontal axis, so it will be positive. But for third and fourth quadrants, we are measuring these angles clockwise. So those angles are going to be negative. And that's why you can't say that these two measurements for the arguments are the same. They are going to be different depending on which quadrant you are. So you need to pay very close attention to the signs and the value of the arguments that you're given. Let's do an example. Find the complex conjugate of Z equals minus root 3 minus I in cis form. So we want to find Z star. What is this? So what we want to do is, first of all, identify what will be the complex conjugate of that number. The complex conjugate is going to be minus root 3 plus I. So if we want to write this number in cis form, we need to figure out in which quadrant this number is located. So minus root 3, let's say it's over here. And then 1 is going to be here. So the number Z conjugate is going to be located here. In contrast, just to put it as reference, the original number Z should be around here. It is a reflection around the horizontal axis. Now the number that we want in cis form is this one. So we need to figure out what the magnitude is, and also we need to figure out what the argument is going to be. Now the argument, principal or regular, they are going to be the same in this case because we're talking about an angle that is in the second quadrant. So what we want to do is find the modulus. So let's start with the r. R is going to be the square root of 3 squared plus 1 squared, and that is 3 plus 1, 4. So r is equal to 2. Now for the argument, assuming we don't have a calculator, I can write the number Z star as 2 common factor of minus root 3 over 2 plus 1 over 2i. So with that in mind, the value that I have here should be the cis function of the angle. Now I need to figure out which value of the angle has a value of cosine equal to minus 3 by 2 and a value of sine of 1/2. Now that angle is going to be related to 30 degrees. So in our original diagram, where is that 30 degrees located? 30 degrees are going to be located right there. So the angle that we want is actually 150 degrees. So the final answer, Z conjugate, would be 2 cis of 150 degrees. Now, I want to use this example to show you one more property. Look at the position of the original number. The original number is Z, is right here. If we wanted to calculate the principal argument of this number, we would start at the positive x-axis and go all the way following the shorter path towards where the number is. In this case, because the Z conjugate and Z are a reflection of each other, then this angle is also going to be 30 degrees. So the principal argument of Z is going to be also 150 degrees. So this is going to be 150 degrees. However, because we're measuring clockwise, this is going to be negative. So notice how the principal argument of a number is of opposite sign from the argument of its complex conjugate. So this is a very important property. If you want to find the argument of a complex conjugate, but you only have the argument of the original number, then all you have to do is change the sign of that argument. Now to finish, I have summarized all the main points of this video towards the left, and I hope that this is a start for you to getting comfortable using the different notations, cis forms and Euler's form, and also to understand the difference between the argument and the principal argument. And maybe you can already think of different properties that each of these two types of arguments are going to meet.